So we are going to talk about how to get a Z-star critical value. But in order to get a Z-star critical value, we need to remember something from chapter 2.
Oh.
The standard normal distribution. The standard normal distribution. That was the distribution where the Z-scores lived. It had a very specific mean and standard deviation. Does anyone remember the mean and the standard deviation for the standard normal distribution? The mean is 0 and the standard deviation was 1. Very good, very good. All right, so we have our standard normal distribution that has a mean of 0 and a standard deviation of 1. Bless you. Now, we have the 68, 95, 99.7 rule. Anybody remember what that is about?
Yes.
What is the 68, 95, 99.7 rule about?
Between the first two standard deviations, there's 68% of the data.
Perfect. If I go out one standard deviation, then I have captured 68% of the data. Okay? So 68% of data is within one standard deviation. Absolutely true. What's the 95 about? If I go 2 standard deviations, then I have captured 95% of the data is within 2 standard deviations. 95% of the data is within 2 standard deviations. And what if I go 3 standard deviations? Then I have captured 99.7% of the data. That's within 3 standard deviations. Now, isn't it interesting that I'm using that word captured from way back in chapter 2? I'm using it now, and that's one of the words we've been using with our with our confidence intervals. So it kind of seems like this goes together, doesn't it? Oh, imagine. So check this out, you guys. It actually does go together exactly. Think about your point estimate as being the middle. It's at the 0. Okay? It's at the mean of 0. Your point estimate is the middle. Your standard error, square root of p hat 1 minus p hat over n, your standard error is the standard deviation value, okay? How far you go is based on the Z-star critical value. How many of those standard deviations are you wanting to go? If you want to be 95% confident, which is the most common confidence level, then you should go out about 2 of your standard errors. So your Z-star critical value would be like 2-ish. I only say 2-ish because it's not exactly 2. There's an exact number that we'll get to in a minute. But if I want to be 95% confident, then my Z-star critical value would be about 2. Because that's how many standard units, standard errors, I want to go to capture that data. If I just want to be 68% confident, then I just need to go out 1 standard error. If I want to be 99.7% confident, how many standard errors should I go out? I should go out 3 standard errors. So remember this formula from yesterday. P hat, that's your point estimate. That point estimate is basically in the middle where the 0 is. Your standard error is the value of each of those standard deviations. It's how far each of those standard deviations are away. And then the Z-star critical value is how many of those standard errors are you wanting to go to capture the middle percentage. So if you want to be 95% confident, then your Z-star critical value would be 2. Because that would mean you would want to use 2 standard deviations so that you could capture that middle 95%. That's basically how Z-star is formed, or that's where it comes from. So, how do you calculate it? Because yes, You probably could figure out what it is if you want to be 68% confident, it should be about 1. 95% confident, it should be about 2. 99.7% confident, it should be about 3. But there's tons of other confidence levels you might want to be. Maybe you want to be 90% confident, so how are you going to find that? Okay, obviously if you want to be 90% confident, it should be a number that's somewhere between 1 and 2, right? If you want to be 98% confident, it should be a number, the Z-star critical value should be somewhere between 2 and 3, right? Because we're again, 68, 95, 99.7. If we're trying to fit it in there, then it would be in between here. So how do we get that number? So the way we're going to get that number is going to seem a little strange, but hopefully you'll catch on after a couple of times. So we're going to do several of these. So here is a picture, right here is a picture of the 95% confidence interval's Z-star critical value. So again, think about in the middle here is your point estimate. Here's your point estimate. You've calculated some standard error, some standard deviation, but you got to know like how far do I want to go out? So you decide on a percent confidence. You decide you want to be 95% confident. What that means is that you want to capture the middle 95%. So this percentage in the middle is 95%. Now you guys already know that that should be about 2 standard deviations, okay? So I'm going to show you guys now how to get the exact value, and that's going to come from your calculator. So if I am 95% confident that I've captured the data because I am talking about the middle 95% of the distribution, that word was like blah. If I have captured the middle 95% of the data because I'm looking at the middle 95% of the distribution, then what percent have I not captured? 5%. Now here's the deal. 95%'s in the middle, and I have not captured 5%, but there's 2 sides that I have not touched. The lower side and the upper side, the lower tail and the upper tail. If there's 5% that has not been captured, then that means that 2.5%'s on the lower end and 2.5%'s on the upper end. It's just half on either side. Does this make sense so far? Okay. So if I'm capturing 95% of the data, therefore being 95% confident I've got it right, then I've got 2.5% that I haven't captured on the lower side and 2.5% that I have not captured on the top side. That means that each of these tails of not being captured has an area of 0.025. That's just me taking 2.5% and changing it to a decimal. So there's an area down here of 0.025. We're going to focus on this lower area right here. This lower area is 0.025. Now, back in the day, back in chapter 2, if I knew what the area was and I wanted to know what the boundary was that cut off that area, I could find it using inverse norm. I know the area and I want the cutoff. I can use inverse norm. So if I use inverse norm here, and I put in that lower area that is not being captured, so the 2.5% that is not being captured, then I've got that area. The mean of the standard normal distribution is 0. The standard deviation is 1. What that's going to tell me is what z-score cuts off the lower 2.5%. And that will be exactly my z-star critical value. Now, if you use this lower area, you're going to get the negative version of the z-star critical value. But because the 95% is the middle and it's symmetric, then your positive z-star critical value is just the positive version of the number you get. So go to inverse norm on your calculator. You guys remember where it is? second vars. Second vars, and it's number 3. Second vars, and it's number 3. And this is your inverse norm. Put in that lower area that did not get captured, which is 0.025 or 2.5%. Okay, so 0.025. That's the percent or the proportion of the lower area that did not get captured. The mean is 0, and the standard deviation is 1. This is going to tell you what the negative version is of the Z-star critical value. It's basically how far below the point estimate you would go to capture the middle 95. And so you should be getting 1.96. Are you guys getting 1.96? Yes. Okay. So 1.96 is how far below the point estimate you need to go. That's how many standard errors below the point estimate you'll want to go. That's also how many standard errors above the point estimate you want to go. Yes, ma'am?
I had a negative, is that?
Yep, so you're getting a negative because we specifically used the lower one. And so it is a negative 1.96 when you use the lower one because it's on the lower end of the interval. The positive version of that same exact number is just how far you go on the upper end. Okay. Now, the Z-star critical value is how far from the point estimate you're going to go in that many standard units. So we can just drop the negative. Okay. So your Z-star critical values are always going to be positive. Even if you see a negative there, it's just because you're looking at the lower end just to get the number, but they're both the same number. One's just positive, one's just negative. So the Z-star critical value for 95% is 1.96. Now I have the best news ever for you. Oh, first of all, before I tell you the best news ever, first of all, do you notice that that's really close to 2? Yeah. Okay, because it's supposed to be, right? Remember, the 68, 95, 99.7 rule is a rough estimate. That's why this isn't exact, but it's really close to 2 because it's supposed to be, because the middle 95% of the data is captured by 2 standard errors or deviations. Okay, here's the really great news, you guys. Z-star critical value is based on a standard Z-score. This number will never change. So if you just say to yourself, self, the Z-star critical value for 95% is 1.96, don't forget it. You'll never have to recalculate this because it will never change. The Z-star critical value for 95% will always be 1.96 because you always have to go about 2 standard deviations to capture that middle 95%. That's what this is saying. Okay? Okay, let's practice finding some other Z-star critical values. Okay? Again, I promise you guys that once you know the Z-star critical value for a certain percent, it will never change, but I don't expect you to memorize them all. Okay? Because at any moment, I could throw a different percentage at you. So you got to know how to do it, but just know that 95% is pretty common. Just saying. That one you use a lot. All right, so we're going to find the Z-star critical value for 80%. Here we go. I always draw it just because it helps me see it visually. If I am capturing the middle 80%, I know I need to go more than 1 standard unit, which would be 68%. But I don't need to go as far as 2 because that would be 95%. So I should be getting a number that's somewhere between 1 and 2 standard units. If I am capturing the middle 80%, what percent is being missed on the lower side? 10%. What percent's being missed on the upper side? 10%. Now, just for ease of calculation, I'm just going to use this lower area. It just makes it easy. So what would be the area of that section there? 0.1. Perfect. You guys are doing great. So I'm going to do inverse norm of that lower area of 0.1. The mean is 0, standard deviation is 1 because I'm on a z-score distribution. And this is going to tell me how many standard errors to use to capture that middle 80%. It should be somewhere between 1 and 2 standard deviations, so it should be somewhere between 1 and 2. You're going to get a negative, but you can just drop the negative because you're going to go both negative and positive. Okay, so you could just drop the negative when you get z-star critical values. What'd you get?
1.28.
You guys are awesome. Let's do it again. I need the z-star critical value for 96%. Okay, so I'm 96% confident that I've captured the truth because I've gone some amount of standard deviations. This should be bigger than 2 because it's bigger than 95, which is about 2. So this should be bigger than 2. All right, what percent is being missed on each side? 2% is being missed on each side. For just the sake of using the lower side, just because it's easier, the area of that would be 0.02. Inverse norm. Area is 0.02. Mean is 0. Good. Standard deviation is 1.
I don't want to talk to you either.
Right? Okay. Oh, there you go. What'd you get for your z-star critical value for 96%?
2.05.
Hey guys, look at that. It's bigger than 2. Should it have been bigger than 2? Yes, because that's more than 95%, which is the one that is kind of about 2. All right, cool. One more.
1.4.
Whoa, kid. I got 90% in the middle. If I've got 90% in the middle, what percent am I missing on either side? I'm missing 5% on either side. Again, just for ease of using not... Here's the deal, you guys. You can use the upper cutoff, but then you have to add these two areas together and get like 95% and blah, blah, blah. It's just easier to do this and drop the negative, in my personal opinion. If you want to do it the other way, you go right ahead. All right, so inverse norm. The area here, it would be 0.05. The mean is 0, standard deviation is 1 because it's a standard normal z-curve. Now, this should be less than 1. I'm sorry. This should be less than 2, but more than 1 because it's between the 68 and the 95. So, what'd you get? All right. Look, guys, this one is a little bit special. This 90% confidence level, z-star critical value is a little special because it's right there on the edge of being 1.65, 1.64. Usually, it's very common to go ahead and use 1.645 for this number. Most of the rest of them, you can just do 2 digits, 2-digit decimal. This one is a little bit cantankerous, if you will. Cool. What questions do you guys have about z-star critical values? Again, what these are telling you is how many of the standard errors are you going to use? And that helps you know how far out from the point estimate to go. That's what these are for. Okay, cool. Well, then you guys are now ready to make a confidence interval. This is the problem from yesterday about Barack Obama's Twitter followers. Ms. Lakey wondered what proportion of Barack Obama's Twitter followers are male, so she selected a random sample of 500 of Barack Obama's followers. In the sample, 308 are male. That's exactly from yesterday. We already verified the conditions are met from yesterday, so we're going to create this interval. We want a 93% confidence interval. I love throwing curveballs. So, you guys need to calculate the 93% confidence interval z-star critical value. Be careful here with your math. Especially if you're trying to do it in your head. because y'all's heads are a little crazy. So if I got 93% in the middle, what percent of my data is on each tail that is not captured? 3.5%. Okay. All right. I'm proud of y'all. Look at you. So that means your area that you're going to use would be 0.035. So you're going to do your little inverse norm calculation. Area is 0.035. Mean is still 0. Standard deviation is 1. Still a z-score. So what is your z-star critical value for 93%? 1.81. Perfect. All right, here we go. We constructed an interval, you guys. Yesterday, we talked about the formula. It is the point estimate, which is p hat, plus or minus the z-star critical value, which you now know how to find, times the standard error, which is the square root of p hat, 1 minus p hat divided by the sample size. You guys have all of the data. You have all of those numbers. You just have to plug and chug. So let's do that. P hat, that is the sample proportion of male followers. 308 out of 500. That is your p hat. 308 out of 500. Plus or minus your z-star critical value for 93% we just found. That's 1.81. Times the square root of, all right, guess what? P hat is a fraction at this moment in time, but I don't know about you. I don't like fractions underneath a square root sign. That makes me a little anxious. So I think it would be really nice if we would just find out what this is as a decimal. So if you just want to go ahead and find out what 308 divided by 500 is, that might make your life a little easier. I believe it is 0.616. All right, cool. 0.616 times 1 minus 0.616.
384.
Okay, 0.384. There you go. Looky there. I don't even have to write that one. I'll just put that. 0.384. Perfect. Amazing. Divided by, and your sample size is 300. 500. I said 300, didn't I?
Yeah.
I lied. It's 500, isn't it?
Yeah.
Your sample size is 500. Your sample size is 500, Miss Lakey. Okay, got it. I don't know. I'm writing the wrong things today, but I'm saying them right. I don't know what's going on with my brain. All right, cool. So here we go, you guys.
You just did it again.
What did I do?
You're writing them right, but you're saying them wrong. You said the opposite.
Wow. Y'all, if I pass out, please call someone. Okay. All right, cool.
I know CPR.
Thank you. Yay! Ah, okay, so we just got to keep simplifying this thing, you guys. This is scary looking. We just got to keep simplifying. So I'm going to go ahead and turn this p hat into the decimal, 0.616, plus or minus 1.81. Okay, all of that junk. Go ahead and just calculate all that right there. All that right there. 0.02175? Perfect. I want to point out what parts we have right now. We have the point estimate, which is 0.616, plus or minus the z-star critical value, and we have our standard error now. So this is the standard deviation, basically, of the distribution, and we are going out 1.81 of those standard units in order to capture 93% of the data. Guys, once we multiply these two numbers together, we will have the margin of error. Okay? So let's go ahead and do that. I'm going to go up here now. So 0.616 plus or minus, we just need to multiply the z-star critical value times the standard error. That will give me the margin of error. What do you get? 0.039. Perfect. So, visually we have 0.616 in the middle. We need to add the margin of error, which is 0.039. And we need to subtract the margin of error, which is 0.039. And that's going to give us our low estimate and our high estimate for the percent of followers that are male for Barack Obama. What is the low estimate for this data?
0.577.
One more time.
0.577.
0.577. What is the high estimate?
0.655.
0.655. Perfect. There is our confidence interval, you guys. So here's my question to you. Are the majority of Barack Obama's followers male or female? It would appear male. We are 93% confident that the true proportion of male followers is somewhere between 57% and 65%-ish. So yeah, it would look like he's got a higher proportion of male followers than he does female followers. Does this make sense?
Yes.
Do you guys have any questions on how to construct a confidence interval? How to get a Z-star critical value? Very good. There's one more thing that we might need to do, and it is finding a particular sample size to be within a certain margin of error. So let's say I say to myself, before I take the sample, that I want to have a certain margin of error. I don't want my margin of error to be bigger than 10% or 5% or whatever. I don't want to go out too far from my estimate. So I come up with my desired margin of error. That means that the actual margin of error, which is made up of the Z-star critical value and the standard error, so just real quick, this is the actual margin of error. If I want my desired margin of error to be something, then I want that desired margin of error to be bigger than or at least equal to the actual margin of error. So I'm trying to figure out here if I want to be a certain percent confident and I want to be within a certain margin of error, how many people should I talk to? So the only problem here is how do I get a sample proportion before I take a sample? Can't really do that, right? So P hat is going to be a guess value for the sample proportion. And if I use P hat equals 0.5, that's the middle, then that'll give me the biggest number that I should need to use to make it happen. So I'm just going to use a guess of 0.5. And then I'm just going to do a lot of really scary looking algebra. Do you guys like algebra?
Yes.
Oh, yeah, you do. All right, let's do it. Tattoos. Suppose you want to estimate P, the true proportion of McKinney-Boyd High School students who have a tattoo with 95% confidence. You want your margin of error to be no more than 0.1. So that's your desired margin of error. We need to determine how many students should be surveyed. So we're going to take our desired margin of error and we're going to set it greater than or equal to our actual margin of error. We're going to plug in what we know and then use algebra to solve for the sample size that needs to be taken. We want our desired margin of error to be 10%. We don't want our margin of error to be any more than 0.1. So, Z-star. Does anyone remember the Z-star critical value for 95% that never changes in your life?
1.96.
1.96. That will be the true answer every time from now on for the day you die. The square root of P hat. I have not taken a sample yet, guys, because I'm trying to figure out how many students should I talk to. So I don't know P hat yet, but a safe guess would be go middle of the road. So I'm going to use P hat of 0.5. So 0.5 times 0.5, because 1 minus 0.5 is also 0.5, divided by n. Algebra, solve for n. How do you do it?
Multiply.
First step is divide both sides by 1.96. That's going to cancel the 1.96 on the right side. 0.1 divided by 1.96. What is 0.1 divided by 1.96? 0.051. That has to be greater than or equal to the square root of, okay, watch this. I'm going to do this step right here. 0.5 times 0.5 is 0.25. Algebra's fun, isn't it? This is why Algebra 2 is a prerequisite for this class. All right, you guys, what do I do next in order to get that n by itself? I need to square both sides here. Squaring both sides, that's going to clear my square root out. I'm moving up here. What is 0.051 squared? 0.0026 has to be greater than or equal to 0.25 divided by n. What do you do now? Multiply both sides by n. 0.0026n is greater than or equal to 0.25. Last step. Divide both sides by 0.0026. n, my sample size, has to be greater than or equal to whatever that is. 96.15. Okay, so time out. How many students do I have to talk to? 97 or more. 97 or more. Because the sample size has to be greater than or equal to 96.15. So I got to go up every time on this. Cool? Cool.